Okay, so I'll start talking about the experimental evidence for de Broglie hypothesis, and this is what we call particle diffraction. So this one is first done by Davisson and Germer. So they are American physicists, and I think what was later called Bell Labs, they were conducting these experiments there. And at the same time, it was also done by Thomson. This is not J.J. Thomson, this is his son. And because this experiment shows the wave nature of a particle, which is electron, it is like said that Father Thomson discovered the particle electron, and Junior Thomson discovered the wave nature, wave electron. So the experiment is something like this. I have like a sample. So let's say this is a sample. And as you know, for waves, we are sending waves, and then we are like probing what comes out, exactly like X-ray diffraction. And in the case of like a Davisson and Germer experiment, we have something like this. Like electron comes in, right? There's like some kind of like a electron gun, which we do not care about, and something comes out, and from what comes out, we put a detector, right? And we see if there's a peak as we change the orientation, right? This is the angle. I think I want to call this, let me call this theta. So what they can do is they can determine the kinetic energy of electron, right? This is the gun. You can just it's like a cathode ray tube. By just tuning the voltage difference, you can increase the kinetic energy of the electron. So here's what they found. So let me first do something like that. So this is, okay, the problem with this plot is how it is represented. It's not like a Cartesian plot, it's more like a polar plot. And here we have so this is incident electron like this. So this is incident. And if you put your, for example, if you put your detector right on the top, you have like a peak. But on the top, we are expecting what comes out to come out exactly like we send it. So, and as you change the orientation of this detector, maybe I can choose it. Like here, for example, angle 0. There's like angle 10. This is angle, I don't know, 45, angle 50, and this is angle 90. Okay? And here, depending on angle, you have something like that. Okay? Maybe more like something like that. What this means is if you put your detector to here, there will be a very large return of photons, whereas if you put your detector to here, right, there will be a very small number of electrons. And this one is for, you can see, if you send electrons with 40 volts. So this is the kinetic energy. So the second one is, let me not give all of them, but maybe somewhere in between, around 54 volts. You do exactly the same experiment, but what you see is something like that. There's a peak, and it's something like that. Okay? And so this angle, maybe I can do it. And yes?
Energy versus what?
So energy is fixed for each experiment. Energy is like, for the first one is 40 volts, second one is 54 volts. This is, you are just tuning the angle, right? Like you are putting your detector in like different locations and you are plotting as a function of angle. But you are plotting is in like a polar plot. What this means is, for example, the first one. So if I put here, there will be almost no electrons detected. If I put here, you can see like there's like a corresponding angle. I don't know, something like this. If I put my detector a little bit higher, there will be like something like this. There will be another dot. If I put my detector a little bit higher, there will be something like that, right? And the angle you have is like this theta. Is that clear? Unfortunately, it's like a complicated way to represent the data, but we have to deal with this in physics. Sometimes things are not perfect. Yes?
In y-axis, it is intensity of energy.
Yes, in y-axis, it's actually radial coordinate is intensity, right? In the polar coordinate, like polar coordinate is like you have angles. For example, if you have like a circle in polar coordinates, you have like constant for all angles. Say if you have like something like this, right? So this is polar plot. Everybody knows polar, how to draw things in polar coordinates, right? So this is what it is. If something is 0, you are closer to the origin. If something is large, you are away from the origin. So that's the polar representation. And if you increase, you can see the thing about here is, so there's like a, here is like a peak, and this peak is exactly like the interference peak we expect from, like, for example, X-ray scattering, right? For some angles, because of like these waves, they interfere constructively. As a result, there's like an increased intensity, and that's the peak of interference, which we'll come to in a little bit. And if you increase the energy even more, you have, again, something like that. I think it's like coming like that and something like that. There's this, again, this peak, but it is not as dominant. And this one is, for example, 68 volts. Good? Now, how do we understand this experiment? So, from the experiment, the data suggests, okay, we have this angle, right? This angle is 50 degrees, so data. I need two things from the data. First, the angle, theta is 50 degrees, and the second is kinetic energy, approximately 54 volt. Now let's go back to our sample and like model it more carefully. So here's my sample. Maybe something like that. Let me put it here a little bit. And electron comes in, something like that, and electron comes out. Obviously, for this kind of scattering, there must be like some planes, right? And these planes are not parallel to the sample surface, right? Like this is what we call like Bragg planes, because these are formed by atoms, and we can think about atoms to form planes. But in this, because of this scattering, it suggests that these planes of scattering are not parallel to the sample surface. Then I can just, by looking at the scattering, I can tell this is how scattering is supposed to happen, right? These are my Bragg planes. And how do I know this? I know this because electron is supposed to come and reflect perpendicular to Bragg plane. Is that clear? I think hopefully that's simple. And let's use two things. Now I can pull this aside. Now I know this entire angle is 50, then this is going to be 25, this is going to be 25, and this entire thing, which is what we care for example, X-ray scattering, is going to be 90 minus, because this entire thing is 90, 90 minus 25, which is going to be what? Like 70, 65 degrees. Now let's use let's use what we know about X-rays. Like this is, right, this is the unconventional thing. Electron is a particle, but we are going to treat it as if it's like a X-ray, right? Treat electron as X-ray. And does anybody remember the formula for X-ray scattering? Like the Bragg condition? Exactly, something like that. Let me give you that. 2D sine. Let me call this, not to mix with theta I showed, let me call a different angle. 2D sine phi is going to be equal to n lambda. This is condition for constructive interference. And d is a material constant, what we call lattice spacing. And since we know X-rays and X-rays are widely used, how can I determine lattice spacing? I can just do X-ray, right? And so this is lattice spacing. And determine it from X-rays. Basically, before doing this electron experiment, take your sample, put it in an X-ray, determine D, and then bring it back and do the electron experiment. And from here, this sample turns out to give determined from X-ray spectra to be, I think I wrote it somewhere, okay, D is equal to 0.091 nanometer. Okay. I forget the sample, but it is some material which we don't care. Then, and I want to, okay, this is the first peak, right? For the first peak, n is equal to 1 in the Bragg condition. Then 2 times d sine phi is going to be 1 times lambda. And phi is what? In the X-ray, we take the angle that you make with the incidence and reflection plane, right? Which is 65, so this is 65 degrees. So d is known, angle is known, the only unknown is lambda, and the wavelength determined from here is the wavelength of the electrons, which comes out to be 0.165 nanometers, right? D is a length, just multiply with sine of 65, and then that's what you get. Mm-hmm.
How did you find D if lambda is unknown?
So D is like this D. That's a good point. This is D, and this has to do with sample. So what I'm saying is like take exactly the same sample, give it to an X-ray spectroscopist. He's going to tell you D, bring it back, and do the electron experiment. That's what they did. So this is one. So we used wave nature to come up with this. Now let's see if de Broglie's hypothesis is working. Let's use de Broglie. And because okay, what is the energy? Kinetic energy is here, 54 volts. 54 volts is much, much smaller than rest energy of electron, which is what? A good number to remember. It was for 2. For 1? I think.
0.51?
Yes, 0. And what is the unit? MeV, right? So this is much, much larger than this, right? Then we can use classical kinetic energy, which is equal to 1/2 mv squared. And this should be equal to electron charge times the voltage. From here I can solve it for, okay, multiply with m both sides, this is m. Then my P, which is m times v classically, is going to be equal to MEV. I think there's also 2, and I need to take square root. So M is known, electron charge is known, voltage is known. If you put this in, okay, I'd have some number, but we don't care. From here, we can calculate lambda from de Broglie relation, h over p. And this is h over 2mev. And if you put all of these numbers, what I found is 0.166 nanometers. So this is de Broglie's expectation, and this is your experiment. I think that's why these three guys, they got the, I think, Nobel Prize for showing the wave nature of matter for the first time, even though it wasn't a pretty experiment. Any questions or comments? Okay, we have some time. So here our conclusion is matter also behave like wave. Of course, this was the early experiment and it wasn't the pretty, but later things like this have been done for like electron, proton, neutron, like gigantic atoms, and they even did not like a complicated Davisson Germer experiment. They actually did double slit experiment because they have like much better. We have much better technology. We can actually produce very tiny slits, and we can actually like measure the interference. Like for example, today we know electron, for example, has interference from double slit. So does neutron. So does proton. So does big atoms like lithium or like potassium and so on. Now let's think about something called particle in a box, which will be very important toy model for us to understand quantum nature. So let me think about a box. So here is my box, like this. This is the box. And so these walls are infinitely hard. So that means nothing can penetrate the walls. So this is, I don't know. So this is x is equal to 0, and this is x is equal to L. And we know like if, so we need to put a wave inside. But we know if the walls are infinitely hard, then, for example, if this is the amplitude of the wave, we cannot have things like this, right? Then that means there's like some oscillation right at the wall, and that doesn't make sense. So amplitude at the ends should be fixed. Here is 0, here is 0, and the simplest thing I can do is something like that. And how do I determine this? This is lambda over 2 is equal to L. Okay, is that clear? Or I can do, okay, let me shift. Okay, this is a little bit also confusing representation, but by now you may have figured out representing data is like a confusing part of science. So we have to adjust our minds for that. So I shift the 0 to here for the second one. We can also have something like that. And for this one, I have lambda over 2, right? This is lambda over 2, this is lambda over 2, and I have 2 of these, and it should be equal to length of the box. Is that clear? And I can go on like that, and I can have lambda over 2 times n is equal to L. So this is the wavelength, but from the Broglie we know lambda is equal to h over p, or p is equal to h over lambda. Because lambda is given with this, for example, this one is lambda is equal to 2L, this one is lambda is equal to L, this one is lambda is equal to 2L divided by n. Then, like P is going to come with these integers, Pn, let me call it, is going to be h over lambda is 2L over n. This is going to be h over 2L times n. Because wavelength is constrained, momentum is constrained because of de Broglie. Is it clear? Okay. And inside the box, okay, again, so inside the box, we expect non-relativistic speeds, right? Non-relativistic speeds. Then I can consider the energy, and inside the box there is only kinetic energy, there is no potential energy, right? Here we can think about this potential to be infinite here and infinite there and zero inside. So there is only kinetic energy coming from this, and it is going to be E is equal to 1/2 m v square. For some reason everybody is familiar with this, but when I write this like this, p squared over 2m, people got scared. So everybody knows this, right? We are fine. See, this is also kinetic energy, nothing, not a big deal. And if I put this thing, I'm going to have 1 over 2m h square over 4l square n square. So let's write it and clean it up. So this is h squared over 8m l squared n squared. And here n is what? We determine n. For example, here n is equal to 1, here n is equal to here n is equal to n. And n can be 1, 2, 3, ... Any questions or comments? Okay, everybody's happy. Generally people object to this example a lot, but this class is happy. So there are a couple of things that follows from here. So first, as you can see, energy is quantized. And now, like classically, we have continuously any energy is allowed, but when you put quantum mechanics and put it in a box, you quantize the energy. And this is due to de Broglie at the moment. And if you want, so here there's like an energy level. Sometimes, so here's the energy level diagram. Energy level diagram. So this is E1, which is h squared over 8ml squared times 1. We put a second one here. This is E2. So this is n is equal to 2. And let me push this. And there's E ... En. So for example, we have like these so-called gaps, which are forbidden energy, right? You can have energies in these gaps due to quantum mechanics. So this is purely non-classical, right? Classically, any energy is allowed. There's also a second thing. So 2, there's also a minimum energy. There is a minimum energy. Min is obtained for n is equal to 1. For example, for this problem, it is h squared over 8m l squared. And A min is not equal to 0. Classically, I can go and right, there's like a box, for example, I can go and put my particle at rest. And it can have 0 energy, classically. Right? Nothing forbids me from doing that. But quantum mechanically, if we are supposed to have waves or particles with wave nature, we have de Broglie condition, and as a result, we cannot put the particle in 0 energy. So this is sometimes called another terminology to expose you. This is 0 point energy. 0 point energy. This is also quantum. Yes. Yes, this is the ground state, yes. But I didn't call it, I call it min, yes, but I think, thank you. Let me call it ground state. Yeah, good job. Any questions or comments? Yes?
Is this the same result from Schrödinger equation?
Yeah, we'll come to that. At the moment, Schrödinger equation is not required, right? We are that's the reason we are progressing in the historical sequence. So far, there's expectations, people hypotheses, and then there's experiment backing it up. Eventually, of course, this kind of doing fitting waves in box is not convenient. We have to make it systematic, and it'll be what you just said. Yes.
And these are the logic behind orbitals, right?
Yes, the orbitals will come out from this, but of course, we cannot use exactly like this semi-classical around atom, right? There, for example, we have to use stronger tools, and we'll come to that. But I think we should appreciate the pain people had to go through in the early years by seeing that. So let me make a comment, and then maybe we can take a break after that. So this is valid for small as well as big, right? I didn't assume anything about size of particles, right? This is the absolute truth of nature. This is how nature works for small particles, for massive particles, for massless particles. If you put radiation, you have to do this. If you put electron, you have to do this. If you put yourself in a box, you also do this. As a gigantic body, you also have wave properties, but we don't see that. So we do not see this in macroscopic world. For two reasons. One, h is small, so Planck's constant is a tiny number. That's why we don't see things. And the second one is m is large. So if you look at the de Broglie relation, this is h over p, this is h over mv. So you are dividing a small number with a gigantic number. As a result, we don't expect to see that. For example, the gap, right? So we don't use phones in the no phones in the class. So I believe you use okay. So this is a gigantic number. So lambda is tiny for real world, but also this energy gap, if you remember here, so this energy gap, which is order of h square, is also tiny, right? Lambda is tiny, E gap is also tiny, and if this E gap is tiny, right, and the quantum numbers also, in the classical world, we are looking at very large numbers, n is very large. So for example, En plus 1 minus En for this limit is almost 0. And that explains why we don't operate quantum mechanically in real world. Okay?
Why did we take n is very large?
Because we have very large energies, right? If you look at your energy, this is 1/2 mv squared. It's joules. Whereas quantum mechanically, we need to have like electron volts. We have like thousands and thousands of hundreds of, I don't know, millions of electron volts. To reach to that energy, n has to be very large. And a little bit increase in your energy is a very large number plus 1. But a very large number plus 1 is almost a very large number, no change at all. So it changes continuously in classical world. We can take a 10-minute break. And if you come early, we can finish the day early.